All right. Hello, everyone. This is building on Base Appchains with Flashblocks. My name is Chris Hunter. I'm an engineer on the Base team working on Base Appchains. Also, a quick Canada Day to all the Canadians.
And my name is Ryan Morning. I also work on the Base Appchains team as a software engineer.
Hey, my name is Alec. I work with Chris and Ryan on the Base Appchains team. Today we're going to be talking about building on Base Appchains with Flashblocks. So first of all, what are Appchains? You can think of Appchains as dedicated block space for your application. We support low-cost, high-throughput transactions, and they are fully customizable to your application's use case as well. Let's talk a little bit about those customizations. First of all, we support custom gas tokens, so you can allow users to pay for gas on your chain using any ERC20 token of your choosing. We also provide contract allow lists, so you can prevent spam on your chain and preserve your precious block space for your core contracts. We also have account abstraction support as well, with support for Smart Wallet and ERC 4337 Bundler and Paymaster.
Okay, and one of the last kind of primary issues to solve with app chains is typically like app chains used to mean kind of more siloed experiences. And the solution that we have here is like fast bridging to and from Base, which is actually really powerful when you think about it. Fast bridging in, of course, is kind of standard for other chains as well, but fast bridging out kind of removes one of the main friction points a lot of app chains would see where, I don't know, bridging in and you think, oh, if I bridge into this game, maybe my assets are stuck there for 7 days for a withdrawal period. Also, with what we'll jump into, like a 10-second withdrawal means app chains can really start to feel more like traditional apps where, you can try out a game, you can withdraw back to Base, and be back into the large ecosystem of Base with all the liquidity, all the users, et cetera. So really that's like the main pain point we wanted to solve. And how we did that is through OP Enclave, which is a modification to the OP stack. Basically, it proves the output via a trusted execution environment, or TEE, and that's what gives us our lightning fast withdrawals of about 10 seconds. Looking a little bit closer at OP Enclave, AppChain blocks are executed by the TEE. We're using AWS Nitro. Basically, the TEE will execute and then sign its output state. This is then posted back to Base for the withdrawal, and no fraud proofs or ZK required. So, although ZK, we're super excited about for sure, the 1 second Base block times of AppChains are not yet, sufficiently. They're too quick to basically prove with ZK yet, but we're keeping an eye on that space. This is the withdrawal flow. So we'll just kind of step through the whole thing here. Basically, a user on the app chain, say they want to withdraw back to Base here, they'll submit a withdrawal transaction to the sequencer. At that point, the proposer and the batcher, which are just standard OP stack components, will become aware of that withdrawal. The batcher's job is to basically submit commitments to the transactions that the chain has included in its blocks. So the batcher will submit the batch. At that point, the safe head, which is just like basically where the current state of commitments are, advances. So with the safe head advance, the proposer is now in a position to submit its output. And so what it needs to do now is to basically call the TEE within AWS Nitro. And for the enclave to recompute the block, because we run these TEs in a stateless manner so we can scale to N app chains, we need to include the execution witness. And what that basically is like all the state touched during execution of the block that the sequencer had, we include that in the request to the TE. So then when the block is re-executed, the enclave has all the information it needs to actually advance that state. At the end of the block, basically the TE has its output. It will return that to the proposer, which then submits it to Base. And that would mean that we would have a withdrawal. That is, all app chains have their own basically like bridge contract, but they're all managed or communicate with the system config global contract. And that validates and stores PCR zeros. And PCR0 is basically, it's a hash of the code and the initial state within the TE. So then you're sure what the TE is running. And that will accept signers. As we mentioned, the TE will return a signature. With that signature, you know that signature came from a specific PCR0, and that's what that's what validates or proves the withdrawals for app chains. So basically, when a withdrawal happens, you can be sure, it was OP Stack or Optimism that did the state transition. Therefore, it is a valid block. And of course, all blocks kind of build on the previous one, of course. So additional tool we added into OP Enclave is basically the PCR0 verifier. It just allows you to basically measure the code within OP Enclave, and then you can verify what's accepted in the system config global contract on chain. So basically, you can be sure that Optimism is what's running within the TE and proving the output. So how to integrate with this system? Basically, you can build your own UX, of course, and we also provide on-chain kit UI components, which just basically allows you to bridge tokens in and out of the app chain. But either way, 2 seconds to bridge in, 10 seconds to bridge out, and your apps have a lot less friction.
Okay, so we'll get a little bit into Flashblocks and what are Flashblocks. So Flashblocks are going to be ephemeral blocks that will allow us to have 200 millisecond block time and real-time UX for on-chain applications. So on Base Appchains, we have a base block time of 1 second. We can split that into 5 ephemeral blocks of 200 milliseconds, and then you'll be able to start to get pre-confirmation data from those Flashblocks. So what does this really look like under the hood? So we have a typical sequencer here that you would see in Optimism. You have your consensus layer in charge of keeping the canonical state of the chain updated, and then your execution layer, which is building blocks and then returning those blocks back to the consensus layer. So what did we add that's new? So added new here is going to be the rollup boost and the new external block builder. And so we'll kind of get into like what the role here of rollup boost is. So rollup boost is going to be in charge of multiplexing the engine API calls to both the proposer. You can think of the proposer as the typical sequencer that we used to have, now upgraded with rollup boost, and the new external builder, which is also building blocks. So this starts to look like the proposer's OP node will trigger some block building by sending out an engine FCU call, fork choice update, and it'll multiplex that both to its internal execution layer and the builder's execution layer. At this point, the builder will start broadcasting those Flashblocks, those ephemeral Flashblocks. And after a while, the OP node will, after 1 second, it'll reach out for that built block, so it'll multiplex out that engine get payload. That block will actually get validated with the internal OP geth, but it has already validated its own block, so that's cached. And then we'll update the chain state. So how can we start retrieving this Flashblocks data? Well, we have the new Flashblocks aware RPC. The Flashblock aware RPC is going to come with some new Flashblock specific methods. The two that are interesting to call out is the Flashblock get transaction receipt with the pending param, and as well as all the other standard Ethereum JSON RPC methods that are working out of the box. You can also stream real-time Flashblocks updates with the WebSocket API as well. So what does this look like for an app? You'll see the client can use the existing receipt RPC to get pre-confirmed receipts, right? So the client will send off some ETH SynRaw transaction over to the sequencer. That'll respond with a hash. We'll poll for that get transaction receipt, and then we'll return the receipt. And all of that will be pre-confirmed from those 200 millisecond Flashblocks. We're also looking to support EIP 7966, which is the new ETH SynRaw transaction sync. We can kind of see how this cuts down a lot of that wasted time from the asynchronous calls, right? So in that first flow I showed you, we send off the SynRaw transaction, and then once we get the hash, we have to pull back out and wait for the receipt. Some of that time can be mitigated because at the same time that we have the transaction execution, the receipt is already available. So with the new ETH raw transaction sync, we batch all that up, and we cut transaction and submission and confirmation time by 50%. And then we also remove that extra need for polling in the clients. This gives that more responsive feel that a lot of people are used to, and that closer to Web 2 user experience. Also, the ETH raw transaction sync is just using existing RPC methods, so it just works as is.
So you might be wondering, what can I build with Flashblocks and Base Appchains? Well, we see a lot of our current customers are gaming customers, so they take advantage of our low cost and high throughput transactions to put partial or fully on-chain gaming. And we also see arts and culture. So for example, crowdfunding platforms that require lots of transactions, as well as real-world assets and DPIN apps as well. So we answered the what. Why should you build with Flashblocks and Base Appchains? Well, first, it's fully customizable out of the box. We have native support for custom gas tokens, contract allow lists, and as well as interop with Base, nearly instant bridging and withdrawals. Second of all, you also get Coinbase integrations, such as Flashblocks, On-Chain Kit, Smart Wallet, and Paymaster, with more to come. Third, high throughput transactions, where, for your use case, maybe using blobs for DA is cost prohibitive. With our infrastructure, we allow you to send transactions at fractions of the cost of using blobs. Additionally, our 200 millisecond block times unlock real-time low latency apps and provide a user experience very similar to traditional Web 2 apps. So you can get started today, actually, because all our infrastructure is compatible with the standard EVM tooling. So everything you use today for your apps, such as Foundry, WAGMI EVM, should have support out of the box for Base Appchains. We provide a standard and a private RPC for you. They have different rate limits and access to different methods, such as the debug namespace. You're also able to access, deploy, and manage your Base Appchain through the Coinbase developer portal. And for mainnets, we're currently in private preview. So a quick demo we have right here. We built a demo app called Base Appchains Bakery. This showcases the power of Flashblocks and Base Appchains. How it works is essentially you have like 10 seconds, you spam spacebar as fast as you can, and each spacebar is one on-chain transaction. And the kind of like pastry you bake depends on how many transactions you can get through in that time period. So as you can see here, I'm spamming spacebar, and you can see the transactions show up on the bottom of the screen. In the 10 seconds, I get around 37 transactions confirmed on-chain with a 90% cost savings compared to blobs for DA. Finally, we're going to open it up for Q&A, and we also have a QR code for the waitlist if you are interested in this product.
Hi, thanks. You mentioned the PCR0 for the OP enclave. These app chains are operating in a T, and so there's a different set of security assumptions there. How does an end user of an app chain get the attestation for the execution? How do I take a transaction that happened in an app chain and get back to the source code that's actually running in that T?
Right. Okay. So that, I guess it would be like a withdrawal, I guess, or are you saying? I mean, okay. So the app chain will, periodically also put its output through a proposal. It also does that when there's withdrawal, so people can withdraw within the 10 seconds. But once it's within that output, you obviously need the information of like what's on chain. So like you get the state there. You can then view. You might have to. It depends how far you want to go back, but you could basically look at assuming you can. Okay, so you have the state hash within the output. You now need to know that optimism is what said that this is a valid state given kind of like some initial block you want to kind of prove from, I guess, right? Once you have that, though, you basically need to go up the certificate chain to know that AWS Nitro was the one that did the state transitions. So within the system config global contract, like we manage what PCR zeros are being added. That's like a permissioned signer we control. We've added OP Enclave there, so you would be able to then basically verify the PCR zero within the TEE is OP Enclave. The signature within, so basically, another level, that's what's happening, because we don't want to post the full enclave attestation with each output. We basically get, the enclave will create a signer. That signer's local inside of the enclave. And then when it signs an output and sends it to the proposer, that's the signature we include. So when we get that signature, the system with a global contract looks at, okay, is the signer approved? And if it's approved, therefore that means that it was within a TEE that had a valid certificate chain. And if it has a valid certificate chain, that PCR zero is what? And then you could use the little kind of tool we have there to see, okay, that it is running OP Enclave.
Okay, so on a high level, if I'm going to want to trust this, but I want to verify, I follow those steps approximately to verify that my trust assumptions are holding in the app chain.
Correct, yeah.
Great,
Yeah.
thank you.
Thank you.
Okay. Any more questions?
Yeah, there's also a blog post that goes into the kind of what you need to do to validate something like that. So it's on the Base engineering blog with a bunch of other good content. All right, yeah, thank you.